Okay, so once again, thank you very much for people online, but so could not hear my first couple of sentences. I just mentioned that this will be a research-focused session on unconventional hydropower, and we focus on the role that this unconventional hydropower can have on grid flexibility. We're going to have three speakers, three young researchers, either last year's PhDs or early postdoc, and so I will not waste more time with the introduction. I will already jump on the first presentation. First speaker will be Stefano Cassano, Dr. Stefano Cassano, actually. He's from HSSO in Switzerland, and he's going to talk about increasing operational flexibility of hydropower application to Laron station and other use case. Just give me 30 seconds to introduce better Stefano. So he received a master's degree in electrical engineering from the Polytechnical School of Genova in Italy in 2018. And as part of the Erasmus program, he also conducted research in the University Catholic of La Louvain-la-Neuve in Belgium. He also held a PhD in electrical engineering from Paris Paris Tech University PSL that was earned in 2022. So since 2023, he is currently a postdoctoral researcher in Switzerland and HS. Stefano, the process is yours.
I go there?
You can go there.
Okay. So, thank you very much for the introduction and thank you for the invitation. It's really an honor for me to be here today presenting this presentation about Laras, which is an unconventional hydropower plant in France, which works with tidal. So, okay. All right. Okay, let's check. So again, my name is Stefano Castano. I'm a postdoc researcher at Offshore SSO in Switzerland. And this presentation is a part of an ongoing project, which is the European project called Story, which I think will be presented the session of tomorrow by my colleague from UPC, Alexander Resas. So, as a power system engineer, I will start this presentation by introducing shortly why the power grid needs flexibility in the future and outline the role of hydropower plants in particular. Then I will move to the challenges that the hydropower plants have to face in the future, and I will also discuss some solutions which have been proposed in the project. Then I will move to the focus of the presentation, which is the Laran's hydropower plant, and I will show how this plant is usually operated to see what are the critical operations that perhaps we can extend beyond the current practices. And then I will talk about two use cases where we will be testing some technologies such as hybridization with battery. And these two use cases are in particular the tidal generation shifting and frequency regulation. Finally, I will draw some conclusion. So, as you may know, the electric power system is normally operated with a large share of conventional generation. So conventional generation refers to mostly thermal, hydro, but also nuclear power plants that are usually coupled with electrical generators, and therefore they are dispatchable. So this means that besides providing electricity for the grid, they also provide a series of services that are very helpful for the grid to ensure its stability and reliability. So today with the energy transition, we are going in the sense of replacing most of the carbon-intensive generation with stochastic renewables, such as PV panels or wind turbines, that by definition are weather dependent, therefore they are stochastic and they are not dispatchable. So these renewables introduce actually in the grid a lot of variety in terms of power generation that at different time scales that will require for the remaining conventional generation more short and long-term flexibility. Therefore, the remaining conventional generator will be called to increase their need for flexibility. In particular, they will be asked to provide more services such as, for example, frequency regulation and grid balancing. That means that we want to keep the grid frequency at 50 Hz, so this generation has to play a bigger role to balance this frequency, but also we have backup and spinning reserve, which because as we may know, one of the key feature of the grid is the inertia, so we need the spinning rotation of the machines, and then also load following, which means we should provide the capability of increase the power to match the demand of power. Now, hydropower is the largest source of renewable electricity worldwide, with more than 50% of the total renewable generation. Hydropower plants are dispatchable, and that means that they can contribute to the grid flexibility in both short-term and long-term flexibility. Regarding the short-term flexibility, hydropower plants can provide fast regulating power. Usually, hydropower plants can increase their production of about 20% of the nominal capacity per minute, and they also provide fast startup times thanks to the lack of thermal time constant compared to like fossil fuel-based hydropower power plants. Then, for the long-term flexibility, some of the plants can provide storage, for example, the case of storage hydropower plants. Okay, so the future challenges for the hydropower plant will be that operating this plant in the future grid will require upgrades to handle the increased operation duties of the plant. So among the proposed solution or technologies is worth mentioning two technologies, which are the variable speed and the hybridization. So the variable speed refers to the coupling the frequency, the grid and the generator frequency to have a more flexible control, which means that usually, for example, the pumps are operated at fixed speed, which means that we cannot really change the speed of the pumps. And therefore, with variable speed, perhaps we can operate in other working condition and perhaps increase the efficiency of these units. And with hybridization, I refer to coupling a battery energy storage system with the plant. So hybridization will be the focus of today's presentation, so I will spend some other words on it. So this is the concept of an hybrid hydropower plant, which basically, again, means coupling a local battery with the power plant that are connected to the same SCADA system. The advantages are multiple. For example, the batteries can reduce the regulation duties of the hydropower plant. That means that can decrease the fatigue, for example, of the mechanical component of the plant. Then another advantage is that it can increase the regulation capability because the battery are very fast to produce power. So before I was talking about 20% per minute for hydropower plants. For the batteries, we are talking about 2000% in seconds. So they are really fast. And then, of course, batteries can store energy, so we can use them for store energy and use it later when the demand is more. Okay, so we arrive at the main character of today's presentation, which is Laurens. Laurens is a tidal hydropower plant, and with its 240 megawatt capacity, it was in the 1966 when it was commissioned, the first and therefore the largest tidal hydropower plant in the world. And then in 2011, actually, they commissioned another tidal hydropower plant in South Korea. So now it's the second one in the world, but it's still quite big. And the plant is equipped with 24 bulb units, so 10 megawatt each, and they feature four-quadrant ability. That means that they can be operated as turbine, as pump, but also they can turbine in both ways, and they can also pump in both ways. The nominal head of the utility is 6 meters, so quite low, because yeah, it's tidal. So and then we have a nominal discharge of around 170 cubic meter per second of discharge per unit, and a total generation of around 490 gigawatt hour per year. So besides producing power, the plant is also important because it's a node for shipping. So we have like 20,000 boats per year that pass through the Larance River, and is also a point of interest for tourists, for tourism. So we have tourists, and also like regarding the nature, a lot of variety of species and animals. Yeah. So why a tidal hydropower plant is because in this region that I forgot to mention, we are in Britain, we are in Dinard, which is close to Saint-Malo. And in this region, we have the highest tidal range in France, with an average of 8.2 meters and a maximum of 13.5 meters. And we also have a large reservoir, which is given by the Larance River, that has 184 million cubic meter of water and spread over more than 20 kilometers upstream, resulting in a basin area of around 22 square kilometers. Now, how this plant is normally operated? This plant is normally operated in two ways. So the first operation cycle is called simple effect, or ABB generation, which means that we use one-way tide utilization. So perhaps, okay, I can point, nice. So this means that the basin is filled at rising tide, and then the water is turbined when the sea level decreases. So to better understand this, sorry. Okay, I will use my hand, sorry. So we take, for example, in consideration the left side figure. We have in the solid black line the sea level, and in the dashed line the basin level. So if we now consider the right hand graph, we can see that okay. So we can see that when the tides increase, we actually store some water in the basin, and then the water level is kept constant until the point that the gross head, which is the difference between the two water level, is high enough to produce some power, and therefore we are in this part of the graph where there is like the turbine operation, and so we produce some power. Sometimes, instead of keeping the level of the water constant, what we can do is that we can increase the head of the water upstream, in the sense, in the basin level, by pumping some water. This allows to produce even more power when the tide is falling. So in this operation, we have the minimum head for the turbines, which is around 1 meter and 20. So below this level, the turbines don't produce power, but instead the water is discharged through some orifices. And the maximum reservoir level that can increase by pumping is 1 meter and 75. Sorry. Perhaps. Okay, so the other cycle is called double effect, or ABB and float generation, which is a two-way tide utilization. That means that the water is turbined at both tidal rising and falling tide. So this means that compared to the previous case, when we are in the, now it works. Okay, nice. When we are in this part, so when the tide is falling, we actually, yeah, sorry, we are here, so the tide fell, so the basin is empty. Now, when the tide is rising again, we can also turbine in the opposite direction, so from the sea towards the river. And uh, and then after, okay, we continue the normal operation, and we can also provide another kind of service, which is pumping, the reverse pumping boat, which is towards the basin to the sea to decrease the head of the basin in order to extract more power for the reverse pumping mode. And this operation actually allows to spread more the production throughout the day compared to the case before, because before we had more, let's say, zero point power production. Now with this operation, we can spread the power production more. And the minimum head for the reverse turbine mode this time is 1 meter and 70. So this slide shows the share of the operation of this plant. So most of the time the plant is operating in the first mode, so the ABB generation with accounting for the 60% of the total operation. Then the reverse pumping it's quite uncommon, so around 0% of the operation, so almost never used. Then we have the float generation, which is the reverse turbining, which account for 2 to 6% of the total operation, and only when the tides are really high, so above 12 meters. And then we have the direct pumping, which is the pump when the pumps want to increase the level of the basin that happen from 15 to 20% of the operation. And then we have the free discharge that accounts for 20% of the operation. And another thing is that no pump is required when the tidal range is above 7 or 10 meters. So now we saw this kind of operation, and we can draw some conclusions. So first of all, the first is quite obvious. So since this is a tidal hydropower plant, the power production depends on the tidal cycles. So it depends on the nature. So we don't really have flexibility in that. And the second point is that the plant is used only for power production, and therefore it doesn't really provide services to the grid, for example, frequency regulation. So now the question we ask is how a battery can a battery actually help to extend the operation of these plants, and how? So to answer this question, I will introduce 2 use cases. The first one is about the generation shifting. So we saw that traditionally the plant is operated these 2 ways. And the idea is to implement a battery to basically shift the part of generation from the tides toward the peaking periods, which means somehow adapting the needs of the plant to the human activities more than the natural cycles of the plant. And then the second point is to spread the tidal generation through the day to avoid zero generation hours during the day. So the benefits of that, or one I already said it, so is to align the generation with the grid needs more than natural cycles. The second is to improve the dispatchability and the flexibility of the plant, because we want to make this plant to behave more like a conventional hydropower plant, so a controllable generation. And third, it enables the battery actually, it can be used also to provide other services, for example, frequency regulation. So the idea is very simple. So the working principle is to use the battery to store some of the energy produced by the turbine, and then use this energy later. So for example, if we consider the 1 unit, instead of producing the maximum power, we can, for example, reduce the power which is injecting into the grid, and use the other part of the power to actually charge the battery, which can be then used later when needed or to spread the power production. So now the question we want to answer is how big is the battery is going to be, or better, how we size the battery in an optimal way to also provide a good control. So to answer this question, we formulate this preliminary optimization problem, which basically aims at sizing the battery, but also find a way to control this battery in an optimal way. So the formulation is the following. So we want to, in general, optimization problems are in the sense of minimizing some costs and subject to some constraint which are related to the operation of the battery. So in particular here, what we want, we have the function cost, which is this one, which is composed by two terms. So we have the capex and the opex. So the capex are the initial capital investment. So we want to minimize actually how much we are going to pay for the battery in terms of power and energy. And then on the other side, we want to maximize, so we want to minimize minus these terms, which means we want to optimize the OPEX, which are the revenues from the battery. So in other words, what I'm saying is that if this is the power of the hydropower plant, we want to maximize the cost from the power we produce. So we have on the left-hand term, we have the power produced by the hydropower plant, then B is the power produced by the battery, and then we multiply that by the spot market price. And then we impose some constraint on the battery, so we want the battery, so the capacity of the battery, the state of charge of the battery to be within certain limits, and also don't exceed the battery power. So the result of this optimization problem would be these three variables, which are P bar, E bar, and B, which are basically the size of the battery in terms of power and energy, and also B is the optimal battery power trajectory. So basically how we are going to control the battery. Okay, so now we have the battery and we think about use also this battery to provide other services. And one service could be frequency regulation, because we saw that the hydraulic machine work at fixed speed, so we cannot really use them for control the frequency of the grid. So the idea is to implement a frequency control loop strategy and eventually also implementing the battery. The advantages are, of course, we can benefit from ancillary services market. That means that we can, let's say, take profit of it because these services are actually paid. And then we can support the renewable energy integration and also enhance grid reliability and security. So just to give an overview how normally a hydropower plant is controlled to provide frequency regulation. So hydropower plant usually implements a speed governor, which basically controls the rotation speed of the machine to follow a design value. For example, the grid frequency of 50 Hertz. So we have this is called a speed governor, which is this one in the figure, and it implements a PID controller that basically translates the difference of frequency between the 50 Hertz and the speed of the machine, and translate this difference into a guide vane opening. This means that if we have an imbalance, for example, a drop in the frequency in the grid, the controller tells the plant to give more power by opening the guide vane. This is for like conventional hydropower plant. In the case of Laurens, we have about turbines. So instead of having just the guide vane, we also have another control organ, which is the blade. And usually the two are related by what is called the on-cam curves. That is the best combination of the guide vane and the blade opening that result in the highest efficiency. Then we have the droop characteristic that tells how much power can the unit provide. provide, sorry. And then we have the servo motors and rate limiter, which are not drawn in this graph, but they are also in the controller. So for an for a hydropower plant to provide frequency regulation, it is important that it fulfills what is called the pre-qualification test. So this test basically, let's say, investigate the ability of the controller to provide the service, but also the stability. The test, it consists in imposing a frequency deviation on the plant and then to see how the plants react. In particular, the plant has to deliver the 50 and 100% of the shared power within 15 and 30 seconds without exceeding some boundaries. In other words, it doesn't have to oscillate. And the power that it's providing is set based on the droop, which is defined as following. And basically here, the lower the droop is, the higher the power the hydropower plant can provide. So now, this is the idea of implementing also a battery. So how can a battery can help to improve this frequency regulation? So the methodology is the following. We have the grid frequency, and we give this grid frequency to the hybrid hydropower plant. And then we have an hybrid controller, which we have to design, that basically want to split the frequency between the battery and the hydropower plant. So one idea could be to give to the hydropower plant the smoothest variation of the frequency, so that the hydropower plant can regulate in a smooth way and therefore reducing the fatigue of the mechanical component. The battery instead can take the harshest variation because it can provide fast power. So how we design this controller is basically a really interesting topic, a research topic, which was also the subject of my PhD. So here I put some reference where I investigate how a battery can actually decrease the fatigue on a certain kind of hydropower plants regarding the fatigue on the penstock, which is the pipe that water the turbine. So to conclude, we saw how hydropower plants can contribute to enhance the flexibility of the grid. I show how the Laurens hydropower plant is normally operated, and pointing out the two critical aspects, which are the fact that the production depends on the tidal, and that the plant is only used for production and not for regulation. Then I present two use cases to extend the operation of Laurens, and I show how we can preliminary size a battery for the case of tidal generation shift. And then I also provided an example of how battery can increase the operation of the service of frequency regulation. And finally, to conclude, I would say that this battery implementation, in my opinion, is worth to be studied to increase the flexibility of this hydropower plant. So thank you very much for the attention. If you have any question, I will be happy to answer them.
Thank you very much, Stefano, for this very interesting presentation. So we have a couple of minutes for question. Are there any questions from the audience here? Or online, you can either write it in the chat or open your mic. But here we have a question.
Yes, thank you very much. My name is Nejana Chundabak. I'm from the Faculty of Electrical Engineering. First of all, I would like to say that the presentation was very, very nice and very informative. I have been to this plant 35 years ago as a tourist to visit it, but I've been studying electrical engineering in that period, and it was very attractive for me to see what else. And what I want to know is, are there any possibilities for implementation of some of your results? what is the attitude? What is the company thinking at the power plant? They certainly know about your results.
Yeah, we are working this European project together.
Are there any plans to implement something like this? Do you have a battery, a certain strategy for?
Actually, this research comes from the fact that they ask us like some ways to improve the operation. So this was my part, which is regarding the battery. So the idea is eventually to size a battery because of course when you do that you have to think about the cost. So if it's worth to implement a battery. So the results will tell us if a battery is a good way to improve the operation of the plant. But there are also other, I mentioned variable speed, for example, which also need an upgrade because we have to basically to change the frequency converter to operate at different speed. And battery, I hope we can implement this battery, but it was something that was asked from EDF, which is the operator of the plant.
But your PhD was 3 years ago, so that means that the other researchers who are still working on this research question.
Perhaps, yeah. I mean, my PhD was on hybridization in general. So I took another use case. I was not working with the Larans. It was on another topic, but in general, my research is on the hybridization. So depends on really the case of the hydropower plant, the needs of the hydropower plant. So in this case, we find that the critical aspect of the plant was that the plant was not able to basically produce power continuously. So the idea is, okay, if we want to upgrade the plant, how we use the battery, and we come up with the solution of like use the battery to spread the production. And then once you have a battery, you use for multiple services usually to take the benefit from the battery. So
depending on the control strategy. Okay, thank you very much.
Thank you very much. And one of your PhD was even implemented, right? In Fogel.
Yeah, exactly. Yeah. But it's
It's a different one.
It is different case, but the hybridization is something that now we are studying for increasing the flexibility of the plants. Yeah.
Stefano, congratulations! Excellent presentation. Down to the point. And unlike the previous lady here, I have been several times, even recently, to Laurence and Saint-Malo, which is an exciting plant since I'm leading the tidal range research in the UK, and we are following very closely the work related to what you've been working on. Could you tell us some thoughts on how you see your research being implemented in general beyond Laran's case that you just showed us here?
As I was saying, okay, it really depends on the use case, and therefore you have to spot the critical operation of the plant and then think about how you can use the battery. Because of course the easy answer would be the bigger the battery it is, the easy, okay, so we can use for everything. But actually the cost of the battery now is still decreasing, but it's still high. So you have to think really well about how much you want to invest for a battery. If you have a lot of money, okay, I suggest to buy a battery and then see what happens. But then here the point is really to optimize the size of the battery, optimize the operation of the battery, because you may know that when you do that, you have to accomplish 3 steps basically. The first one is to size the battery. So you want to gather some information from the plant in terms of production, energy, to say, okay, I will size the battery in this way. Then there is the control of the battery. in long-term control, which is called state scheduling. So you want the battery has to be charged in a certain period, because if you need the battery, then the battery is discharged, the battery is useless. And this is the second point. And then you have the real-time control. So you have to develop another type of control that really adjusts the power of the battery. But this controller is really specific on the operation of the plant. Before I was mentioning my research that was on the fatigue reduction of the penstock. So I really studied just the case of the penstock, and I developed this controller that basically somehow model the fatigue, so the pressure within the pipes, and it tells when the fatigue is too high to go to give the power to the battery, for example. So it really depends on the case.
Yeah, thank you very much. Obviously, on a similar case to Laurence, perhaps you could extend it to other projects like
Sure.
Korea.
Sure.
But offshore. But also, are there any examples that have been implemented as far as you are aware of this idea?
This is quite a new research topic. So far I know there are few, but there are no hybrid hydropower plants. So perhaps there are. Yes. Sorry, sir. I mentioned that because it was in another European project where we were working on hybridization. So we have few cases for now, but we hope to have more in the future.
Thank you very much.
Very quick one, because we are running out.
Okay. Did anybody look at an economic case in that case?
Of course.
There'd be more generation to earn more money and get more revenue and pay off the battery.
The core of the organization is basically market.
Yeah, but can you tell if it's gonna be 10 to 20% more, or is that a figure?
For the moment, no, because actually this project just started 8 months ago. So this is really a preliminary work. So I cannot.
Thank you.
Thank you very much,
Thank you.
Stefano, for your very insightful contribution. And if you have more questions, please either at the end we have some few minutes or in the coffee break. So I'm pleased now to introduce our second speaker. Please, Robert Nijhuis. I don't know if that's correct. Nijhuis from University of Groningen in Netherlands. Robert will talk about developing a novel underwater pumped hydro storage system. And let me again read a little bit of his biography. So Robert is a PhD candidate at the Engineering and Technology Institute of Groningen at the University of Groningen. And he holds a master's degree in industrial engineering from the same university. He has a background in finite element methods analysis and design optimization. So he's actively involved in the development of an ocean battery design at the Ocean Grazer company. And his latest work presents a comprehensive water-to-wire framework to capture the operational dynamics of an underwater pumped hydro storage system in an open water environment. So please, Robert, the floor is yours.
Can you switch the?
You should have. Yeah.
Oh, perfect. Thank you, Elena, for the introduction and also for the invitation. Hi, everyone. My name is Robert Nijhuis. I will present to you something about developing a novel underwater pumped hydro storage system that we do in the north of the Netherlands. It's also called the ocean battery system. Well, part of my research was in collaboration in the DOSTA research initiative. That was actually one of the first multidisciplinary research initiatives initiated by the TNO, and together with the University of Utrecht and the University of Utrecht, Groningen, and in collaboration with industry, we started this research initiative, which focused on developing offshore storage and transport alternatives, where we looked into the North Sea area region for the Netherlands. There are 4 multidisciplinary approaches where we mainly looked into offshore energy storage, offshore hydrogen production, and energy transport alternatives, together with future grid integration solutions. So this my work package was focusing on the technical design of the offshore energy storage system. We had also from the Faculty of Geoscience of the University of Utrecht a student that was focusing on nodal network optimization of energy mix of different energy storage systems in the North Sea for a future energy grid. We also had someone from the University of Groningen, from the Faculty of Law, who looked into the future legal framework that we need to develop for the future. And also for the Faculty of Spatial Sciences, we also had a student looking into the marine allocation of the new renewable energy sources, how we could optimize that in the future. So my focus was mainly on the offshore energy storage system. The pumped hydro storage system, for conventional pumped hydro, we use the potential energy to store the energy into the system. Well, this works a little bit different because we have no significant height difference in the Netherlands. Instead, we use the hydrostatic pressure of the surrounding seawater to store the energy. I will explain a little bit more. As you can see in the bottom corner, oops, no. Okay. Well, what you can see here are the main elements of the system. We have a flexible reservoir on the left, which actually acts as a barrier between the external seawater and the internal working fluid. We have a rigid reservoir on the bottom right side, where the working fluid is stored, and it is connected with the umbilical connection to the surface of the seawater to ensure an atmospheric pressure in the reservoir. There's an internal ducting in the system, and we also have a powerhouse holding a reversible pump turbine or a dedicated pump and turbine system. We would expect that this so-called ocean battery system would operate around the minute and hour market, similar to conventional pumped hydro. And we can highlight 3 development phases. Currently, we are in phase 0, where we're looking at the working concept and prototyping, and experimental measurements are being taken. And then the next step would be that we would go into phase 1, as you can see there, where we want to place around a 1 megawatt rated system into a sand excavation lake. Once we would finish that phase, we would go into phase 2, where we want to move and install a new system more to the offshore side, where we would place it on the shoreline somewhere in the Netherlands or in the northern western of Europe. And the final phase then would be what we also looked into, is the case study where we would integrate the system into offshore wind farms. The novel elements of the system that we highlight here are the flexible reservoir and the umbilical connection. That's also something that we did some research on to ensure or to look into what the impact would be on the overall operational transient dynamics of the system. So one of the key features for my research to develop a model framework for the ocean battery system. And a brief overview I wanted to provide first before I dive deeper into this. We have the actual physical system, which you can see in the top. It's controlled by the cyber system, and there's the SCADA and the EMS. And there's a counterpart, the digital twin system, where you can identify the market system model, where we use certain we have forecasting models there to implement when it would operate, how it would operate. We have the different design configurations we can input into this system, and we have some higher order validation models that we can input into our core 1D network model, for which we can simulate the transient dynamics of the system. So I will go through each of these steps briefly. Well, the main part is then the network 1D network model simulation, and I will show at the end. So for the system design, it's actually not one fixed design. We have multiple types of designs that is dependent on the deployment location of the system. So in the North Sea, the average depth is around 100 meters. So for that, we would have a deep water system, which is just embedded on the surface of the seabed. There's also, but if you look into the region that is close towards the Netherlands, the depth is only 30 meters. So instead, we have a different design configuration for that. That's the shallow water design configuration where we embed the rigid reservoir into the seabed to create an additional head for the system. It is also a modular approach at this moment where we can expand the system with different segments to have control over the power to capacity ratio for the system. One of the first steps that we did for the phase 0 was to develop a small scale prototype. It's actually a 2 by 2 meter prototype scaled 1 to 50, where we installed in the top left, you can see the base structure of the system, of the prototype system, where we installed a small scale pump and turbine, which you can see in the middle. On the top right side, we also defined the flexible bladder or flexible manifold, which you can see here opened, and we included also a camera system in there to track its movements during operation. On the bottom left side, you can see the barge system, which we also designed to be able to lower the system to the determined operational depth to be able to do multiple experimental runs. So we could define also the head in the system during the operation for every experimental run. In the middle of the middle bottom side, you can see the umbilical line, which is seen as also on the right side, and you can also see the location, the Eemshaven in the north of the Netherlands, where we performed the experimental results for the first prototype. So one of the main features one of the main objectives for the prototype session was to validate the working concept, also to see what the impact would be on the internal head losses of the system or the dynamics impacted by the novel elements that we added to the system. And also we wanted to measure the overall internal head losses. And then in the end, we wanted to scale up the system with a software that mimics the transient dynamics of the internal prototype and to determine its overall round trip efficiency. So under optimal conditions, the prototype is operating at around 77% round trip efficiency. Yes, you can see here the sensors that we put down at different locations throughout the system to measure its internal head losses. So I will come back to that later. It's one of the validation models that we use as an input to the 1D network model for the simulating the transient dynamics of the system. Now, another key feature is that since we placed the system into an open water environment, that's the goal of phase 3. We need to know what the environmental loading impact would be onto the system. Since we have a flexible bladder, we would want to know if marine biofouling, sand deposition due to scouring, or environmental loads due to waves, swells, and tides would have any impact on the transient dynamics of the system. So that we investigated with additional research. You can see some examples. Well, we mainly focused on wind waves, swells, and tides for the environmental loading. We did some experimental results also for marine biofouling over time. And we, together with the Deltares Institute in Delft, we also performed some scouring simulations and experimental results. For the scouring, you can see here the setup of the system. The video is sadly not working, but you can see that we performed a scaled prototype experimental setup for one side of the system with the flexible bladder in there, the geotubes that would hold the system down, together with a part of the ducting and the base structure as well. But we performed some pressure measurements for different sea states, and we wanted to see the complex interaction between the structure and the seabed over time. We did that for different test conditions for unidirectional flows, bidirectional flows, so for the tidal interaction, and also for once in 50 years storm wave conditions. For different orientations, we looked into the impact of scouring, and then together with the in-house software of Deltares Institute, we also scaled up the system to the large scale dimensions and performed this experiment again for a longer period of time to see if there is any impact of the scouring and standing position. For the waves, swells, and tides, we actually did a different simulation. We included the wave dynamics using linear wave theory, where we defined two main areas in the North Sea region, one in a shallow water region, one in a deeper water region. And there we identified what types of swells the combined impact would be of wave swells and tides on the flexible bladder. Because the idea is that since the flexible bladder would transfer the hydrostatic pressure of the surrounding seawater in a 1-to-1 ratio into the system, if a wave would pass over, there would be a pressure deviation that could propagate into the system and also would result in an altercation of the internal transient dynamics during charging and discharging operation. So we needed to be sure to see what the impact would be of this. So for both regions, we looked at different sea depths, different wave heights and wave periods conditions, and we implemented that into the 1D network model. For the simulation of the system, we collaborated also with Power Vision Engineering as a spin-off company from the EPFL, where we used their 1D network modeling approach to simulate the system. Well, if the three different domains are combined, they're using an analogy for the Simpson software. So we could also simulate for different Francis reversible pump turbine configurations to see well, what would be the optimal size for our system for every phase. Well, to give some an idea of the results that we had for let's say majority operation of the system. On the right side, you can see again the two different configurations that we looked into. We have the deep sea version on the top right, and on the bottom left, we have the shallow water configuration. And well, this is just for showcasing the dynamics. So we actually scaled down the rigid reservoir to be able to show the simulation within in a very small simulation time. So how it would when it would be operating during charging and discharging operation. Well, we showcased all the parameters in per unit. But what you can see here, the main takeaways are that the rigid reservoir itself has an impact on the head variation during operation. So normally you would, for conventional pumped hydro, you would expect a constant head, but actually we do have to deal with a head deviation that is around 15% for the deep water system and around 15 to 25% for the shallow water configuration. That is due to the design of the rigid reservoir elements. And also you can see the deep water version is not particularly impacted by the combined impact of waves, swells, and tides. On the right bottom side, you can see the red line. You can see the small deviations there. That is due to the effect of the external loading factors that we simulated based on our experimental measurements. So yes, these are part of the. This is a brief overview of the steps that we are currently looking into to develop the system, and we are currently looking into variable speed operations and operational control algorithms to also add to this system and expanding it further. So to conclude, well, for the underwater pumped hydro storage system, we look at different design considerations based on the deployment location. We use experimental measurements to perform and to validate the novel elements. Well, we include external loading factors for the open water environment. And for future work, we want to look into more variable speed operations to see how far we can push this system and where we can operate on. On the internal losses, we define also, we expect the external loading to contribute to have an impact of 1 to 2% of the head loss. And well, the overall efficiency, as we see it now from the 1D network model simulation, is around 68%. The relative efficiency of our system. Yeah, that was my presentation. Yes.
Thank you very much, Robert. Very interesting and inspiring work. Are there questions for Robert? I will just. You.
So my question is, you said that you're using different liquid within that system from the seawater. I hope you realize that environmentalists will tear you apart if that is something that can spill and cause problems. So maybe if you could give some additional information about that, or liquid, what it is.
It is normal water that we use. So instead of seawater, we want to avoid that in the system, so use normal water.
And the second question is about that tubing that you said that is used for side pressure. Can you maybe share some information? How do you ensure that there is no seawater input in case of storm and so on? Thank you.
Yeah, so the idea is that the connection is done through geotextile, so it's a multi-layered system where not only so the electronical connection is there as well, together with an air conduit, and it will be connected to a buoy to the surface where it is connected. So that would be designed in such a way that we minimize the spillage into the system.
Okay, other questions, George?
Thank you. Robert, well done, excellent presentation, well done to you and your team at Cranberry University. Just following on from the previous question, a few years ago, one of my predecessors at Lancaster University, Professor Michael French, developed a device called a Lancaster Flexible Bag. And that might be very some information on the internet. Now, I remember a concern, well, predates me, but I remember discussions with him. One of the concerns was the life cycle of the rubber material and the effects on it. Is this something you considered, or are you going to consider it? Because I remember there was quite a lot of discussion at the time, specifically on that weakness point we saw on this device.
Yes, so regarding the material, we're now looking into geotextiles such as EPDM, which is relatively inert. I think according to our research, it is possible to operate underwater, and it has a life cycle, I think, of a maximum of 50 years. I'm correct about that, but indeed it should. Well, we hope, of course, to be able to operate the system for a longer period of time than that. So then we would need to do one or two changes of the material in the end. Yes. So we saw, due to also the biofouling aspect, that there is some marine life growth that would appear on the flexible bladder, for example. And over time, there would be some minor deterioration of the layers, delamination, due to the calcium layers that are in between the material, which the marine bio growth would like to reach. So there is some interaction with the marine growth that we also are looking into. Yes.
Okay, thank you very much, Robert. I think we're running out of time, so I encourage to have a discussion through coffee breaks with Robert and the other speakers. Thanks once again. So our next and the last but not least speaker, Sudesh Dahl from AKH Zurich in Switzerland. He will talk about reservoir sedimentation management in Switzerland for sustainable hydropower under climate change. So we now go back a little bit more into the conventional hydropower, but with a new hidden, doesn't work this? Oh,
Those are additional.
this was yours.
They are the additional slides.
Okay. Okay.
Yeah, that one. This one.
That's the first one?
Yeah.
This one?
That blocked.
No, that's the previous one.
Yeah,
No,
the previous
but-
one is the one, but. And why this is blocked?
There seems to be some
Yes.
Think it's quite.
Okay, so that was just the introduction, so.
Okay. Let me introduce Sudesh. So he's a civil engineer specializing in hydraulic and hydropower engineering with extensive experience in hydraulic design, sediment transport modeling, and sustainable reservoir management. He's currently completing his PhD in hydraulic engineering at ETH Zurich, where his research focused on numerical modeling and reservoir sediment management strategies under future climate scenarios. Sadesh holds a master's degree in water science and engineering from IHE Delft, Netherlands, and a bachelor degree in civil engineering from TU Nepal. His professional background includes roles in hydropower project designs and construction in Nepal. So, Sadesh, the floor is yours.
Yeah.
But maybe let's first see it about them. And why what I was saying before. So we will go a little bit back to more conventional hydropower now, but we will see which kind of hidden opportunities we have to improve storage capabilities in conventional hydropower plants. So in a sense, we will see some unconventional aspects of what we have to see. And we will see some with Sadesh how it's possible to consider sediment management in order to improve the storage capabilities of that.
Just try.
Okay, now it seems to be all good.
Yes.
First yours.
Thank you, Elena, for introducing me, and good morning and welcome everyone to my presentation in this meeting. I am presenting about my PhD research topic, which is the reservoir sedimentation management in Switzerland for sustainable hydropower under climate change. So I'm mainly dealing with the problem of sedimentation in reservoirs. And the conventional way of operating the hydropower reservoirs has been mostly to postpone the problem of sediment to the future. But I am trying to deal with unconventional way of operation by integrating the sediment management strategies to ensure long-term sustainability of hydropower storage capacities. A brief introduction about dams and hydropower in Switzerland. There are more than 200 large dams with about 3,100 million meter cube of water storage capacity. And in terms of electricity source in Switzerland, more than 56% of electricity is sourced from hydropower. And among that, more than half of the hydropower has the storage capacity flexibility, which is indicated by this seasonal energy content of Swiss reservoirs, which shows that the reservoirs are mainly used to store electricity during the summer months, during the high flow in the river, that is utilized during the winter months to balance the seasonal variation of electricity demand. However, in the last 2 decades, the balance of winter electricity has been negative in Switzerland, which emphasizes the importance of more storage capacities in Switzerland. And also, this is a statement from the EU Hydropower Alliance that indicates that about 1 terawatt-hour of flexible hydropower enables the construction of at least 3.5 terawatt-hour of intermittent wind or solar. So this emphasizes that storage hydropowers are essential not only for seasonal flexibility, but also to the flexibility to integrate the wind and solar renewables into the overall grid system. The topic of reservoir sedimentation. This is a simple sketch of a reservoir that can be generally used for hydropower energy generation. And these reservoirs are not only supplied by river water, but it also accommodates the sediment that's inflowing from the upstream river. And this is how the sediment may deposit inside the reservoirs. And the deposition of sediment mainly causes this is how the deposition of sediment may look inside the reservoir, which is the example of the Gracie Reservoir in Switzerland, which indicates a large amount of sediment deposition after the lowering of the reservoir water level. So these are the main consequences of reservoir sedimentation. One of the main consequences is the loss in hydropower storage capacity, which indicates that currently the trend is declining. That means the global water storage capacity, the increase in water storage capacity due to construction of new dams is not compensating the loss in capacity due to sedimentation. And also in terms of per capita, this rate of decline is even more critical. And another issue is the issue of dam safety. For example, this is the example of a reservoir in Switzerland, which has been impacted by large amount of sediment deposition just upstream of the dam. The sediment level was increased up to the level of the bottom outlet, which also impacted the safe operation of these dam outlets, thus causing a problem of the dam safety aspect of the overall dam component. In terms of the cost of reservoir sedimentation, it is estimated that currently the overall cost sums to be around 21 billion US dollar per year. However, only a very small fraction of this cost is being currently addressed. And if no any sediment management measures are conducted, implemented in the operational scenarios, these costs will be mainly postponed into the future generation, thus causing an intergenerational unfairness. So this emphasizes the need to conduct more intensive investigation on reservoir sedimentation, not only to understand the processes behind them, but also to plan for effective countermeasures. And the investigation of reservoir sedimentation can be mainly done by conducting numerical modeling, which leads to the first research objective of my project, which is to conduct the one-day numerical modeling of sediment bypassing scenarios in a case study of Switzerland. Then I am also dealing with the problem of climate change scenarios in the case of Switzerland. This is the plot that indicates that temperature has been rising in Switzerland since the last century, and there are three different climate change scenarios defined for Switzerland, which is the RCP at 25, which is without any climate change mitigation measures. The best case scenario is the RCP 2.6, which is the with high degree of climate change mitigation, and there is also an intermediate scenario called RCP 4.5, which involves moderate climate change mitigation scenarios. And the main impact of climate change on the river discharge in Switzerland is estimated to be a seasonal shift in the annual runoff pattern. For example, the winter discharge may slightly increase as indicated in this plot, and the summer discharge may slightly decrease, thus causing a seasonal shift in the annual pattern of river flow. However, the impact on sediment yield has been highly uncertain, although there are multiple hypotheses proposed. So a case-by-case study needs to be done to identify the impact of sediment yield for all these climate change scenarios, which leads to my second research objective, which is to conduct climate scenario data analysis and sedimentation simulations, in which I focus on a case study, the Reservoir of Switzerland. And regarding the sedimentation rate in Swiss reservoirs, this is a plot from the data obtained from a study in 1998 for 19 different reservoirs of Switzerland. And from this, it can be analyzed that the median rate of sedimentation amounts to about 0.2% of storage volume lost per year. However, this median value has a drawback that it provides equal importance to all these 19 reservoirs, which have a large degree of variance in terms of the water storage capacity. For example, it ranges from the capacity of 0.1 million meter cube to 400 million meter cube. Thus, a more improved estimate of overall reservoir sedimentation rate in Switzerland is necessary. That can be used to forecast a reliable estimate of the existing water and hydropower storage capacities. This leads to my another research objective, which is to derive improved methodology for regional sedimentation analysis, in which I focus on the case of the overall Swiss fleet of reservoirs. And the overarching goal of this research project is to derive improved understanding of existing status and processes, also to demonstrate the tools and methodology to assess the countermeasures against sedimentation, to ensure long-term sustainability under climate change scenarios. So here are the methods and results of my first research objective. A brief introduction to my case study reservoir, which is the Solis Reservoir in Switzerland. This is the location of the Solis Dam in the map of Switzerland. This is the layout map of the reservoir, which is fed by the Albula River, as shown in the bottom right corner. And the main feature of this reservoir is that it has a sediment bypassing tunnel, which is shown as in that red line. This bypass tunnel has the inlet in the middle reach of the reservoir that was constructed in 2012 to mitigate the further adverse impacts of sedimentation. That mainly operates to bypass the incoming sediment away from the main part of the reservoir to release the sediment downstream of the reservoir, thus not allowing the incoming sediment to settle into the reservoir, causing more adverse impacts. And this sediment bypass tunnel is abbreviated as SBT, that I will frequently use in my presentation. This is the picture of the Solis Dam, which was constructed in 1986, and the sedimentation rate is estimated to be around 80,000 meter cube per year. This is the picture of the Solis SBT. And this is the short animation video of the SBT outlet during its operation of sediment bypass. This is about the historical sedimentation profile in the reservoir. And we can see that since its construction in 1986, there has been large amount of sediment aggregation, not only in form of the delta deposition, but also in form of the rise in bed elevations near the dam. And in 2012, the SBT was constructed that has partly mitigated further adverse impacts of sedimentation. And in my case study, I focused on the case of 1998 to 2001 to calibrate the numerical model, and then focused on the case of 2018 to 2019 to conduct multiple scenarios of sediment bypassing simulations in order to identify an optimum solution for the sediment management. So this is the result of my model calibration, which is animation of the numerical simulation of the sediment input from the upstream region. So the upstream boundary is supplying both water as well as sediment in forms of bed load and suspended load. And the aim of this calibration is to match the simulated and measured bed profiles, which shows a good agreement, and also to match the sediment volumes, which is also in a good agreement, thus calibrating the overall model performance. And for the modeling of SBT operation, this is a simple sketch of the different fluxes of the water and sediment through the SBT, and I derived a novel equation as shown in this plot for the flux of bed load that can be bypassed through the SBT in terms of the water discharge and the reservoir water level. And using this approach, I conducted multiple scenario simulations for the sediment bypass tunnel under a given flood wave of 2019 June, which was a 5-year flood event in the reservoir. So these different scenarios were designed for different timings as well as duration of the sediment bypassing operation. So all these scenarios have a different degree of cost related to the loss of revenue generation during the SBT operation, because during the bypassing process, the water cannot be used for the power generation. So I assessed all these scenarios by conducting numerical simulation to quantify uh, how much of the storage capacity can be recovered under these scenarios. So the cost of these scenarios are related to the loss of revenue from potential power generation, and the benefit is related to the additional revenue from peak energy generation in future that can be obtained from the recovered active storage. So I conducted a cost benefit assessment, and the net benefit is computed as the difference of the benefit and cost. So this is the plot of the normalized net benefit for different price ranges of the base energy and peak energy price, where I demonstrate that it is possible to identify an optimum solution of sediment bypassing, which is not only technically feasible but also feasible in terms of the economic considerations. Thus, the numerical model is useful to conduct this type of analysis, also to support the economic viability of the sedimentation countermeasures. I move on to my second research objective, which is the climate scenario data analysis and simulation, which is the case study of the Gigerwald Reservoir in Switzerland. This is the location of the reservoir in the Swiss map. This is the layout map of the reservoir, which is fed by the Tamina River, and it also has an inflow from an indirect catchment called Wistanenthal. This is the picture of the dam, which was constructed in 1978 as a 147-meter high dam with an initial volume of 35 million meter cube, and the sedimentation rate is estimated to be 60,000 meter cube per year. The main sediment problem here is the rise in bed elevation near the dam, which is about 0.5 meter per year. And because of this, the dam bottom outlet has been recently reconstructed to a higher elevation, which required a large amount of cost for those construction activities, mainly caused by the sediment problem. Climate change scenarios in this case study. This is the data analyzed from the HydroCS 2018 project of Switzerland, which provides the future runoff projections for multiple climate change scenarios, such as the RCP 2.6, RCP 4.5, and RCP 8.5. And this plot shows the cumulative runoff evolution under those different scenarios, including their uncertainty range. All of those climate change scenarios have their corresponding uncertainty range as indicated by the shaded part of this plot. I use this runoff data to derive the sediment input into the reservoir by using the validated sediment inflow equations based on numerical modeling. So this is how the sediment input seems like until the end of the century for all these climate change scenarios. And it is interesting to note that in some climate scenarios, there is a sudden spike of sediment input, which is mainly related to the occurrence of extreme flood events associated with the climate change. So using this data and using the validated numerical model, I conducted a numerical simulation of sedimentation until the end of the century. So this is a brief animated video of the numerical modeling progression, which mainly indicates how the supply of sediment from the upstream boundary gets distributed along the reservoir. As we can see, a gradual increase of bed elevation, mainly in the middle part of the reservoir, and also we can see the rise in bed elevation near the dam, which is mainly caused by the inflow of fine sediment from the adjacent catchment. And this sediment deposition is also gradually reducing the water and hydropower storage capacity of the reservoir. So this is how the result looks like at the end of the century in the year 2100. So I demonstrated what kind of sediment management can be done under this scenario. For example, the conventional approach of sediment management in this reservoir has been to limit the inflow of high sediment concentration from the adjacent catchment Westamental, which is adapted to be a concentration threshold of 4 gram per liter. And I demonstrated multiple scenarios of that concentration threshold. For example, by reducing the threshold to 2.5 gram per liter, it is possible to reduce the bed aggradation near the dam by a high amount, as shown by those multiple numbers of bed elevation rise near the dam. And I quantified a metric called sediment management efficiency, which is the mitigation of potential impact of sedimentation against the impact without sediment management. And using these modeling results, I again quantified the cost and benefit metrics. For example, the cost of this sedimentation countermeasure is related to reduction in water volume supplied to the reservoir. So, for example, 28% reduction in water volume will cause a reduced bed aggradation of 11.5 meter with a sediment management efficiency of 44%. So these cost and benefit metrics can be used for a more detailed cost benefit analysis to support the optimization of sedimentation countermeasure in the long-term sustainability of the bigger world reservoir. And this approach can also be applied to other reservoirs worldwide. Finally, I defined a improved methodology for regional sedimentation analysis. Here, I briefly summarize the different parameters related to reservoir sedimentation. The main one I'm defining here is the trapping efficiency, which is the ratio of the deposited sediment volume to the inflowing sediment volume. And the main driving parameters for this trapping efficiency are the capacity inflow ratio, bed load to total load ratio, and the reservoir operation ratio, which is defined as the degree of fluctuation of the reservoir water level. And this trapping efficiency is defined as a function of these 3 different parameters. So I defined a new equation for the sediment trapping efficiency based on the existing data from the field, as well as supplemented by additional data generated from numerical modeling of multiple synthetic reservoirs that typically represent the reservoirs of Switzerland. So this is the new equation that I derived for the sediment trapping efficiency, which is a relation between the 3 different parameters that I mentioned in the earlier slide. And these are the largest reservoirs in Switzerland in terms of the energy storage capacity. For example, the Grande Distance is the largest one, which has a capacity of about 1.7 terawatt hour energy storage capacity. And I identified that 35 of these reservoirs hold 95% of the energy storage capacity in Switzerland. So I focused on these 35 reservoirs to conduct further analysis. And by using the previously derived trapping efficiency equation and the sediment yield estimates from the different literatures, I derived the sedimentation rate for all these 35 reservoirs. And I found out that weighted average rate of sedimentation is about 0.06%, which is in the range of 0.018 to 0.1%. And using this sedimentation rate, I computed the future projection of water storage capacity in Switzerland. For example, currently the water storage capacity is 3,100 million meter cube, which may reduce by 4.6% by the end of this century. Similarly, I also estimated the hydropower storage capacity, which is estimated as 7,600 gigawatt hour currently, and it is estimated to reduce by 4.2% by the end of this century. So with this, I would like to conclude all my research activities. In the first part, I derived a novel equation for the sediment bypass tunnel the flux of sediment through the sediment bypass tunnel that can be used in the numerical modeling approach. And also I demonstrated a cost benefit optimization methodology for sediment management. I found out that with increasing severity of climate change, it may cause a slightly less sedimentation, but this is only limited to the non-glaciated catchment that I was dealing with. And I demonstrated the simulation of sediment management scenarios and how it can support the quantification of the cost and benefit metrics that can be used for a more detailed cost benefit analysis. And I finally derived a new methodology for regional sedimentation estimation with a new equation for the sediment trapping efficiency that I used to improve the estimate of sedimentation rate in Switzerland. And eventually the main finding is the methodology and tools to support the planning of sedimentation countermeasures, which will be useful for the hydropower operators, and also improve understanding of sedimentation status and hydropower storage capacities in Switzerland, which may provide useful information for the formulation of various policies related to Swiss Energy Strategy 2050. So with this, I would like to conclude my talk and then thank you all for your attention.
Thank you very much, Sadish, for your very nice presentation.
Yeah.
So I open the floor for questions. Yeah.
Thank you. It's a really nice presentation. I have a question regarding hydrologic data. You use the hydrologic data for climate change, right?
Yeah.
Do you consider the dams in these preparation data?
Well, that data has been derived from the existing database of Switzerland. For example, there is a HydroCS 2018 database that provides the projection of discharge in the river at the ghost stations of Switzerland. So I suppose they have already included these dams and whatever other infrastructures are there. But yeah, that was not directly done by me, but I just used the existing available data.
Thank you.
Yeah.
Thank you very much for this very interesting talk. I was just wondering, so you have a lot of uncertainty in climate change projections in hydrological data, and especially how events affect erosion and sediment input. Did you do kind of a sensitivity analysis to identify which part of your, because it's kind of a simulation chain, contributes most uncertainty, and also most of the hydropower plants have a management system already in place. Yes, so they're flushing out the reservoirs, sediment in the reservoirs every few years. How did you how did you deal with the flushing management that is already in place currently?
Yeah, thanks for your question. Well, in my case studies, I just focused on 2 of the reservoirs, so they did not include those flushing activities. But regarding the uncertainty you mentioned about the climate change, I did numerical simulation, like the climate change scenario data provides the future estimate and the uncertainty range. So there are multiple climate change models within the same scenario. So I conducted a numerical simulation for all those uncertainty range as well, and just derived what could be the deviation from the mean projection value. I did not display here in the presentation, but yes, I conducted those kind of simulations to quantify the degree of uncertainty within each climate change scenario.
Okay, thank you.